So far, we have mostly seen how to use GANs for generating images. While generating images is fun, and it is connected to several important AI research directions, it's immediately useful in only a few niche domains, like making image editing software, where the goal is actually to produce a nice image at the end of the day. A much more generally useful application of GANs is semi-supervised learning, where we actually improve the performance of a classifier using a GAN. Many more current products and services use classification than generation, so I imagine a lot of you would be much more excited to learn about how to build a better classifier than about how to generate images. Object recognition models based on deep learning often achieve superhuman accuracy after they have been trained. Modern deep learning algorithms are not yet anywhere near human efficiency during learning. Consider the Street View house numbers dataset used to train address number transcription models. This dataset contains hundreds of thousands of labeled photos of address numbers. Recall when you learned to read. Your teacher didn't need to take you on a road trip to see a whole city's worth of address numbers and tell you what each of them said. From this point of view, deep learning seems to require a lot more data than people do. From another point of view, we could argue that deep learning isn't getting a fair chance because the entire life experience of a deep learning model is only a group of labeled images. People are able to learn from very few examples provided by a teacher, but that's probably because people also have all kinds of sensory experience that doesn't come with labels. As we move around the world, we see objects in several different lighting conditions, from several different angles, and so on. We don't receive labels for most of our experiences, but we have a lot of experiences that don't resemble anything that a modern deep learning algorithm gets to see in its training set. One path to improving the learning efficiency of deep learning models is semi-supervised learning. In semi-supervised learning, the model can learn from labeled examples like usual, but it can also get better at classification by studying unlabeled examples, even though those examples have no class label. Usually it is much easier and cheaper to obtain unlabeled data than to obtain labeled data. For example, the internet is essentially a free source of virtually unlimited amounts of unlabeled text, images, and videos. To do semi-supervised classification with GANs, we'll need to set up the GAN to work as a classifier. GANs contain two models, the generator and the discriminator. Usually we train both, and then throw the discriminator away at the end of training. We usually only care about using the generator to create samples. The discriminator is usually of secondary importance, and only used to train the generator. For semi-supervised learning, we will actually focus on the discriminator rather than the generator. We'll extend the discriminator to be our classifier, and use it to classify new data after we're done training it. We can actually throw away the generator, unless we also want to generate images. For semi-supervised classification, the generator is of secondary importance, used only to train the discriminator. So far, we have used the discriminator net with one sigmoid output. That sigmoid output gives us the probability that the output is real rather than fake. We can turn this into a softmax with two outputs, one corresponding to the real class and one corresponding to the fake class. If we hardcode the logits for the fake class to 0, then this softmax computes exactly the same probabilities as the sigmoid used to. To turn the discriminator into a useful classifier, we can split the real class into all of the different classes we want to recognize. For example, to classify 10 different SVHN digits, 0 through 9, we can make a discriminator that has 11 different classes in total. Real zeros, real ones, and so on, up to real nines. And then one extra class, the class of all fake images. Now we can train the model using the sum of two costs. For the examples that have labels, we can use the regular supervised cross-entropy cost. For all of the other examples, and also for fake samples from the generator, we can add the GAN cost. To get the probability that the input is real, we just sum over the probabilities for all the real classes. Normal classifiers can learn only on labeled images. This new setup can learn on labeled images, real unlabeled images, and even fake images from the generator. Altogether, this results in very low error on the test set, because there are so many different sources of information, even without using many labeled examples. To get this to work really well, we need one more trick, called feature matching. The idea of feature matching is to add a term to the cost function for the generator penalizing the mean absolute error between the average value of some set of features on the training data and the average value of that set of features on the generated samples. The set of features can be any group of hidden units from the discriminator. In a paper called Improved Techniques for Training GANs, OpenAI was able to achieve an error rate of less than 6% on SVHN, using only 1,000 labeled examples. For comparison, the best previous semi-supervised learning algorithm had over 16% error, nearly 3 times higher. Of course, fully supervised algorithms, using hundreds of thousands of labeled examples, are able to achieve less than 2% error, so semi-supervised learning still has some catching up to do compared to the brute force approach of just gathering tons and tons of labeled data. Usually, labeled data is the bottleneck that determines which tasks we are or aren't able to solve with machine learning. Hopefully, using semi-supervised GANs, you'll be able to tackle a lot of problems that weren't possible before.